x equals 1 over x. Firstly, let's consider x equaling 0. For x equaling 0, we'll have 1 divided by 0. We're trying to evaluate how many times 0 would fit into 1, and we can't come up with an answer for that. So therefore we say that the function is undefined, and there is a vertical asymptote at x equaling 0. If x equals 1, then y will also equal 1. 1 divided by 1 is 1. And so we have the point 1, 1. If as the values of x increase, we're going to have 1 divided by an increasing number. So therefore, the result will become smaller and smaller. So as x becomes larger, the values of y become smaller. You know, as an example, 1 divided by 2 would be 0.5. 1 divided by 5 would be 0.2. 1 divided by 10 would be 0.1. And you can see that that occurs here. So as x approaches positive infinity, the value of y approaches 0. And it does so from what we call above, so just from the positive part. On the flip side, if we take a look around at this section of the graph, the values of x that are greater than 0 but less than 1, then you can see they increase. And this also makes sense. So as an example, if x is equal to a half, then the rule will become 1 divided by a half. In other words, how many halves would fit into 1? And the answer for that would be 2. If you could imagine x equaling 0.1 or 1/10, then the rule would become 1 divided by 1/10. How many 1/10ths would fit into 1? And would get 10. So as you can see, as x approaches 0 from what we call above, so from the positive values of x, the value of y will approach positive infinity. If we look at the negative section of the graph, then you can see it's the opposite. It's the same shape, but it's just been flipped around in this x-axis. We'll begin with x equaling -1. 1 divided by -1 will produce -1. Again, as x approaches negative infinity, you will see that the values are becoming smaller and smaller, that they're approaching 0. And they are negative. If we consider what's happening between -1 and 0 for x, then you can see that the size of these values are increasing, although they are negative. So again, as an example, if we looked at -0.5, 1 divided by -0.5 would be -2. 1 divided by -1/10 would be -10. So we get that same shape. We also have a horizontal asymptote for the standard hyperbola, and that is y equaling 0. There is nothing I can substitute in here for x that will give me a result of 0. You might be tempted to think that to put a 0 in, but 1 divided by 0 is in fact undefined. At no stage would the standard hyperbola cut through the x-axis. Variations of this hyperbola will cut through the x-axis and y-axis when we do transformations, but the standard one will not. It's these properties that we'll work with. Here's a summary of everything. So just to explain this to you again, as x approaches 0 from the negative, so as we come through this way, the value of y will approach negative infinity, and that's seen here. As x approaches 0 from above, or the positive side, then y will approach positive infinity, and you can see that curve. as x approaches negative infinity, so as we start moving in this direction, the value of the curve will approach 0. And as x approaches positive infinity, you can see that the value of y is approaching 0 as well. Our domain. For x, we can have all the real numbers, excluding the asymptote, the vertical asymptote at x equaling 0. So we can say we've got the set of real numbers excluding the set that contains 0. And the range exactly the same. We've got all of these y values from negative infinity to positive infinity, but we're excluding the horizontal asymptote at y equaling 0. So we can write that as the set of all real numbers excluding the set that contains the element 0. So this is the basic hyperbola with some variations in it. A vertical translation of k, horizontal translation of h, and a dilation factor of a. The dilation factor is the size of this a. Let's go and take a look at the effect here. So if a is a negative number, then we'll get the basic hyperbola but reflected in the x-axis. The horizontal translation, the easiest way of working this out is just to take that bottom line, make it equal to 0, solve for x, and then that will tell us if we're moving left or right and by how much. K is the easiest to understand. It's simply a shift of k units. If k is positive, we're moving up k units. If k is negative, we're moving down k units. The domain will be the set of all real numbers excluding the horizontal translation, and the range is the set of all real numbers excluding the vertical translation. Whenever we state our transformations, we need to always do it in terms of dilations, reflections, and translations. Let's look at some examples. It'll make more sense. So I need to sketch this graph. Firstly, the horizontal asymptote. That will be just this end part. There is nothing I can throw in for x that will make this first term here become 0. So there is no way at all that I'm able to obtain y equaling negative 3. Because this left-hand side here, this left term, will always be something. So if I'm subtracting 3 from it, it's impossible for me to obtain an answer of y equaling negative 3. So we have a horizontal asymptote of y equaling negative 3. Vertical asymptote. Let's just take x plus 4, make it equal to 0, solve for x, and so I work out that the vertical asymptote is x equaling negative 4. So straight away what I can do is rule up my Cartesian plane and place in my asymptotes. Notice that the dilation factor is 2 and the actual value of a is a positive value. Okay, so the dilation factor is the size of the is the size of a, and that is a 2, but a itself is positive 2, so that means that there is no reflection. So my basic shape is going to be like this, no reflections. To evaluate the y-intercept, I just simply substitute x equaling 0 into the rule and evaluate that it's negative 2.5. For the x-intercept, I sub y equaling 0 into the rule and I work out that I have negative 3 1/3. So I place those in and then sketch the graph. And here's a summary. We find the position of the asymptotes, find the intercepts, decide whether we have a negative or positive hyperbola. On the set of axes, draw the asymptotes and intercepts, treating the asymptote as the so-called new set of axes, sketch the hyperbola. So what I mean by that is remember that with no transformations, that the hyperbola, if it's positive, around the grid or the set of axes would be like so, and then this part. But if it was negative, it would be reflected in the x-axis, so it would look like this and that. So in our situation, it was positive, and so what I did is I put in my asymptotes and then did that pattern that I described before around the asymptotes. That is what I have in blue. All right, question 11. State the changes that should be made to the graph y equals 1 on x in order to obtain the graph y equaling negative 4 over x plus 2, take away 1, and sketch the graph. Now earlier I said I need to do this in terms of dilations, reflections, and translations. We are dilated by a factor of 4 parallel with the y-axis. So we ignore the sign, we just take the size of what's at the top here, and that's 4. We say it's parallel with the y-axis because every y value has been multiplied by 4. That's the effect of that dilation factor of 4. We've got a negative, so we know there's going to be a reflection. We say that we are reflected in the x-axis. It's always the x-axis. That is, every y value has been multiplied by negative 1, meaning that values that are above the x-axis will now be below the x-axis, and values that were, or points that were below the x-axis will now be above the x-axis. So we are reflected in that axis. Translations. The effect here is that we take every point and move it down 1 position. So we say that we are translated 1 unit down. Horizontal translation, make x plus 2 equal to 0 and solve for x to work out that it is negative 2. So that means that every point is picked up and moved 2 units to the left-hand side. So we are translated 2 units to the left, or if you like, in the negative direction along the x-axis. Sketching the graph, horizontal assy, vertical assy, basic shape, and this is really important. We've got a negative value, so we're reflected in the x-axis, so this shape will now become that shape. My steps, x-intercept, make y equaling 0. Y-intercept, make x equaling 0. So I draw up a Cartesian plane. I put in my asymptotes, so that's x equaling 2 and y equaling negative 1. I put in my intercepts, and then I draw the basic shape. Remember that it has been reflected about. Okay, so looking at the truncus, we have f of x equaling 1 over x squared. Take a look at the graph straight away. Similar type of curve to the hyperbola, except for we have both of the curves on the left-hand side and the right-hand side being above the x-axis. And the reason for that is because of the squaring component. So even if you threw in a negative value here for x, when you square it, it will become positive, so we'll have 1 divided by a positive. So meaning that the overall result will be positive. Let's look at the values on the right-hand side. So if x equals 1, then I have 1 over 1 squared, which is 1. So the point 1, 1, same as the hyperbola. But let's look at a difference now where we have x equaling 2. We'll have 1 over 2 squared, which will become 1 over 4 to produce 0.25. And imagine if we had x equaling 10, would have 1 over 10 squared, which would become 1 over 100. So what you see here is that the values, as x increases, the values of y approach 0 very quickly, much more quickly than the hyperbola. Looking at the values where x is between 0 and 1, if I have x equaling a half, then according to our rule, it would be 1 over a half squared, which will become 1 over a quarter, How many times would a quarter fit into 1? 4, so we would be up here at 4. Whereas the hyperbola would be just 2. So you can see that the values for the truncus increase much more quickly than the hyperbola. And as I explained before, that curve is just mirrored over here, and they're all positive because of the squaring component. So that's the basic truncus, and transformations that apply to the hyperbola can also apply to the truncus. There's a summary of everything. Remember our domain, set of all real values excluding the vertical asymptote, x equaling 0. Our range is different. We can have all values that are greater than y equaling 0. All right, again, we can never achieve y equaling 0, so that's why it's here. So all values for y being greater than 0, or if you like, it's a set of all real numbers that are positive. You can also write it in that notation. All right, state the changes that should be made to the graph in order to obtain this. So in my first move, what I'm going to do is get it into the standard format that I'm used to for a truncus. So you can see what's common here is a 2. It's starting from there, so I've brought out the 2. Now, of course, everything needs to be squared. The x plus 2 is squared, but so too is the 2. So that becomes 4. And now the 4's cancel out to give me this. So I'm going to be working with this one. So we're looking at taking the standard truncus and converting it to this truncus. So it becomes pretty simple. There are no dilation factors. There's no reflections. I have a translation of 1 unit down, and then I take what's inside the brackets, make it equal to 0 to work out the horizontal translation, and that ends up being x equaling -2, so I have a translation of 2 units to the left. Sketch this graph. Now, of course, I'm not working with it in that format, I'm working with it in this format because I know that they are equivalent. Horizontal assy, y equals -1. Vertical assy, x equals -2. X-intercept, I make y equaling 0. Add 1 to both sides. Multiply both sides by x plus 2 squared. Take the square root of both sides. And that gives me plus or minus 1. And then I subtract 2 from both sides to get -1 or -3. And that's shown. The y-intercept, just sub in x equaling 0 to produce -3/4. And then just draw in my shape. Taking a look at the square root function. Just this little symbol here is known as the radical symbol. If there is nothing up here in this small bit, they call it a superscription, then it's just assumed that it's a square root that we're dealing with. But if it's a 3, it's the third root. If it's a 6, it's the sixth root, and so on. So if we've got f of x equaling the square root of x, it'll produce this function here, or this graph here. It has an endpoint at 0, 0, and that's a part of it. So if we take the square root of 0, the result will be 0, so that makes sense. If x equals 1, the square root of 1 will be 1. If x equals 4, the square root of 4 will be 2. And so you can see how we can create that shape. What you'll notice about that is that the domain will be x being greater than or equal to 0. And the range is y being greater than or equal to 0. However, remember that that is just the basic square root function, but we can take the function and transform that around, just like we did with the hyperbolas and truncuses. There's our standard, and the dilation factors and the reflections work exactly the same as they did for the other two types of functions. Horizontal translation is the same, vertical translation is the same. The endpoint will be HK. So take whatever's inside the square root symbol, make it equal to 0, solve for x, and that will be the x value for your endpoint. And then whatever we're adding and subtracting will be the y value for the endpoint. Again, the order of describing the transformations is dilations, reflections, and translations. State the transformations from the standard y equals square root of x going to this. Dilation factor of 3 parallel with the y-axis. So we ignore the sign here for the dilation factor, and it's just 3, so every y value is being multiplied by 3. We write that as so. We've got a negative, so that means that every y value has been multiplied by -1. So consequently, the standard graph has been reflected in the y-axis. In fact, that shouldn't say y-axis, it should say x-axis. That's been reflected in the x-axis. We are translated 4 units up, and we are translated 5 units to the left. Take what's inside here, solve for x, x equals -5, so that means we're moving in the left direction. Endpoint, -5, 4. Our basic shape, we started with this, but we've got a reflection in the x-axis, so it comes down. Y-intercept, just simply sub x equaling 0, we get this exact answer, and that's what you should write down on your graph, but it's approximately equal to this, just so you know roughly how much it is. X-intercept, make y equaling 0, so I've got that. I'll move this to the other side, divide everything by 3, square everything, then subtract 5, and then rearrange it. So I now put in my intercepts, put my endpoint in, and draw away. Notice that for the square root function there are no asymptotes. Let's take a look now at dilation factors that are parallel with the x-axis. So if you have a number immediately in front of the x, so for the 1 over x, if we have a value immediately in front of the x down the bottom here, then that is a dilation factor that we're considering parallel with the x-axis. Same thing for the truncus and for the square root function. If there's a number immediately in front of the x that's within the square root function, then what we have here is a dilation factor of 1 over the magnitude of k, the size of k, along the x-axis. If k itself is less than 0, then we have a reflection in the y-axis. So this is a new idea that we're introducing. State the transformations as we go from there to here. Firstly, we're dilated by a factor of 2 parallel with the y-axis. That's easy. What you'll notice is that there's a 4 immediately in front of the x. That represents a dilation factor that's parallel with the x-axis. The size of it will be 1 over 4. So we ignore the sign, and that is a 4 that's in front of the x, so the dilation factor will be 1 over that 4, so it's a quarter that we end up with, dilated by a quarter parallel with the x-axis. So the effect of that is that every x value would be multiplied by a quarter. This negative, we're reflected in the y-axis. Again, every x value is being multiplied by -1. Translated 1 unit down, and translated 3/4 of a unit to the right. Take what this is, make it equal to 0, solve for x. Horizontal ASCII, y equals -1. Vertical ASCII, 3/4. Our basic shape, we go from the standard hyperbola to the negative hyperbola. That's been achieved by reflecting in the y-axis. So what was here is now there, and what was here is now there. The intercepts, x-intercept make y equaling 0, produce this, y-intercept, x equaling 0. Draw in my asymptotes, put in my intercepts, and then draw that basic shape through. Y equals the square root of x to become this. We're looking at the square root function, but we've got dilation factors affecting both the x and y. So firstly, the half, or negative a half. Dilated by a factor of a half, remember we ignore the sign, parallel with the y-axis. That is, every y value on this original graph has been multiplied by a half. The effect of this -4, dilated by a factor of a quarter, parallel with the x-axis. So now what we're doing is looking at all the points, taking the x values and multiplying them by a quarter. We are reflected in the x-axis. That's due to this negative. We are reflected in the y-axis. That's due to that negative. We are translated 2/3 of a unit up. And we are translated 3/4 of a unit to the right. Solve for x to produce positive 3/4, indicating that we're moving towards the right. Sketch that same function. So my endpoint is 3/4, 2/3, the y value. Solving for x inside here. Y-intercept, make x equaling 0. I get that exact value. X-intercept, make y equaling 0. And I produce x equaling 11/36. What's interesting is the basic shape. I have a double reflection. So this is the standard. Then I'm reflected in the x-axis, and then I'm reflected in the y-axis, so I get that shape. Draw up my Cartesian plane, place in my endpoint, place in my x-intercept, y-intercept, and then draw that basic shape. Just going to give you now a summary of everything. This puts everything all together. Here's the three functions that we've been working with: hyperbolas, truncuses, and square root functions. And now what I've got is the variations of them. All right, we've got an A and the K is happening there as well. Let's look at the A. We ignore the sign of it, and we have that parallel with the y-axis, that is from the x-axis. Every y value has been multiplied by that. If A is negative, then the graph will be reflected in the x-axis. Let's now take a look at the K. So these are the values immediately in front of the x. We're dilated by a factor of 1 over the size of K, again ignoring the sign, parallel with the x-axis. If K itself is negative, then we're reflected in the y-axis. Looking at the effect of the C, then we're just translated C units along the y-axis. So just as you read, if it's positive, it's up; if it's negative, it's down. And the effect of the H, well, it's the horizontal translation. The easiest way of working this out is to take all of that, make it equal to 0, and solve for x, and that will tell you if we're moving left or right. Let's look at another example. Problem 18. We've got this rule. State the transformations from 1 on x to this. Dilated by a factor of 2 along the y-axis, so we ignore the sign. What's the effect of this -4? Dilated by a factor of 1/4, so it's 1 over the size of that. along the x-axis. We've been reflected in the x-axis, and we've also been reflected in the y-axis. We've gone 4 units up and 3/4 of a unit to the right. So 3 minus 4x, make it equal to 0, we get positive 3/4, so that indicates we're moving to the right 3/4. We need to sketch this graph, and then we're going to map the point 3, 1/3, because that is a point that is on this equation. We're going to map that through this set of transformations and see what it ends up becoming. So firstly, just sketching it. Vertical assy, horizontal assy, basic shape after those two transformations ends up being, so it's a standard hyperbola. And then we've got this transformation applied, which is just into the x-axis, and then finally another one, we end up with this shape. So because of the double reflection, we end up where we started from. X-intercept, y-intercept, draw in my asymptotes, put in my intercepts, and sketch. Here's the interesting part. We've got 3, 1/3. That is a point on the original y equals 1 on x. Let's apply the first dilation factor, dilated by a factor of 2 along the y-axis, parallel with the y-axis. That is, every y value has been multiplied by 2. So x is the same, but now we have the 1/3 being multiplied by 2 to give me the new point, 3, 2/3. So after applying this transformation, it's now going to be this point moving to this. Let's consider the next transformation, dilated by a factor of 1/4 along the x-axis, parallel along the x-axis. So this is affecting the x value now. So I take the 3, multiplied by 1/4, the y stays the same. So now this point has been moved to this point. We're reflected in the x-axis, so every y value has been multiplied by -1. So only affecting the 2/3. So 2/3 times -1 gives us this. Reflected in the y-axis, so every x value has been multiplied by -1. So the 3/4 has been multiplied by -1 to produce this. Translated right 3/4. So here again I'm only affecting the x value, so I'm adding 3/4. And so it ends up being 0, -2/3. And then translated up by 4 units, so I'm affecting the y values of the points. And so get that. So what I've just worked out is the f of x equaling 1 on x. This is a point that lies on that curve. That particular point has been moved to this particular point, given all of these transformations. And they are the transformations required to go, remember the original question, from here to here. So a point 3, 1/3 lies on this curve. And then if I apply the transformations necessary to produce this function, that particular point 3, 1/3 will become 0, 3 1/3, and that particular point will fit on this graph. There'll be a point on that graph. That's what I've achieved by mapping that point through the transformations. This is a very difficult question for you to understand, but if you can get your head around it, it really helps you be able to apply transformations on those simpler questions.